Okay, so unit 4 is going to be our last unit for the semester. Actually, we're going to spend the rest of the year talking about probability. 4A is the unit we're going to cover right now. As far as we're going to knock that out notes wise within the week. We'll spend a week doing extra problems and reviewing, and then the following week, before Thanksgiving, we'll try to get that test in, or that quiz. I don't know if it's a test or a quiz, and we'll get that knocked out and be ready to go after Christmas and knock out 4B after Thanksgiving, and knock out 4B. So let me see if I can keep myself going straight here, and we'll get going. So when we start out with basic probability rules, we have the law of large numbers. Okay, so what that means, if we observe more and more repetitions of any chance process, a proportion of the times that a specific amount occurs approaches a single value. So it works like this. If I take a coin and I flip that coin 3 times, there is a chance, 1 in 8, that I end up with 3 consecutive heads. Okay, so do I have the magic coin? Is it going to be the coin that flips heads? Well, it could be if it's a double-headed coin or something like that, or if it's a weighted coin and the weighted coin, weighted side wants to go down. Weighted die, that's what a weighted die has. One side that's weighted, so that's gravity who takes over, and that's the side that gets pulled down more frequently than it should, so therefore the number opposite the weighted side gets that. But anyway, I'm going off on some weird tangent here. So if we talk about, so if I continue to flip that quarter or flip that coin, I could flip it 10 times and I could end up with 7 heads and 3 tails, which is an outcome that's possible. Okay. But as I continue to flip that coin 100 times, 500 times, 1,000 times, the more often I flip it, the closer and closer I will get to its relative long-term frequency, which is going to be that single value that definition talked about. Okay, so what we want to talk about is like when you go to do your first problem in your homework, you're determining if something is plausible. Okay, so what we're looking at number 1 here. So this is where we're looking, if my pen would work. Okay, we're looking at this guy here. For any event, the probability of any event A has to be between 0 and 1. So if we're looking at events to see if they are plausible or not, that's the first thing that we're going to look at. Okay, is that all probabilities are between 0 and 1. The other thing that we have to look for is, and we're justifying if these are plausible, okay, is that all outcomes add to 1. Okay, so when we do this, when we see all the outcomes, we can add them together and it's going to add to 1. We have that complement rule. The likelihood of it comes in different forms. You're going to see me, I'll write it out like this. I'll write the probability of not A, just because that's the way I prefer to write it myself. But the A complement is sometimes used. The A prime is sometimes used. So again, notation wise, a lot of things can be worked there. I just prefer not A. Anyway, that's going to be 1 minus the probability that it is A. I don't know what you just did there. That was cray-cray. Undo that. Where did you come from? This guy right here. What are you? I don't know. You did some magic stuff on me. I don't know. Stop. There we go. Complement rule. 1 minus the probability of A. Again, here at the beginning, it's going to be a little bit vocabulary based. We're going to have to understand what a mutually exclusive means. We have a general addition rule to follow. So here we go. Mutually exclusive. Okay. Are 2 events that cannot happen at the same time. Okay, so for example, I can't be a green and a yellow, a green and a brown M&M at the same time. Okay, I can't be a type O blood person and a type A blood person. Those are events that are mutually exclusive. Okay, another name for mutually exclusive, and we'll throw that one in there. We'll draw an arrow to it. Disjoint is the same thing as mutually exclusive. So again, understanding vocabulary. I don't know why I didn't have that in here, but oh, there it is. I have it right here. If I look at my notes better, okay, down here, mutually exclusive and disjoint. We have that there. I'm cluttering your notes for no reason now. Okay, And we left ourselves a definition. All right, Ted, this is we're off to a great start. Okay, independent is when knowing the outcome of one event does not change the likelihood likelihood. I struggle with this word. Okay, so for example, if I say the likelihood of winning an NFL game is going to be any team, if you just pick a game at random, the likelihood that the home team wins the game is going to be, let's say, 60%. However, if it turns out that I know that I'm picking the Chiefs to win a home game, then that percentage goes up. So therefore, those two events, winning a football game and being Chiefs, those are not independent events, because if I know one, the likelihood of the other is going to go up or down. So that's when we're talking about, or if we look at, if I look at the crash rates of males, let's look at crash rates of teen drivers. Okay, if I know that just crash rates in general, I could find that data. However, I break it down by gender. And I know that those are not going to be independent events, because males would have a tendency to be in more accidents. So therefore, those are not independent events, because being male increases the likelihood that I'll have an accident. So a teen driver involved in an accident and gender are not independent events, because the one event increases the likelihood of the other. Okay. If we see this symbol here, this is going to be my and symbol. It means the intersection of two events. This is my union symbol, or an or. And this is either event or both. Okay, there is a spot up here that I probably need to write. It probably appears in our notes somewhere, and I'm just killing this, but I'll go ahead and write it here, because I have it in my notes from last year and I wrote it here. So we'll try this one, because they are tied together. We'll write it out here. Mutually exclusive events can never be independent. Okay, if I have the green, I have a blue or I have a green M&M in my hand, if I know I have a 50-50 shot of it being blue. So therefore, if I find out that it's not blue, then now my percentage goes up to 100%. So that's what a disjoint means. If it's disjoint, it has to be one or the other. That means it can't be independent, because my likelihood has to change from 50-50 to 100, or it depends on the circumstance. But mutually exclusive events can never be independent. Okay. So example one, distance learning courses are rapidly gaining popularity. It's kind of forced on some people this year, but that's the way it is. Among college students, randomly select an undergraduate who is taking a distance learning courses for credit and record the student's age. Here is the probability model. Okay, so first of all, show that it is a legitimate probability model. So here's what we got to do for legitimacy. We covered this on the front page of notes. It is legitimate if, number one, my probabilities are between 0 and 1. Okay. The second thing that has to be true, sum of all events equals 1. All right, so if we're checking this out, number one, all probabilities between 0 and 1. Is that true? 57, 17, 14, and 12. So therefore, that is true. So we can check that off, okay? Number two, if I add 57 and I add that to 17 and I add that to 14, I gotta pick up my pen and I add that to 12, then that means that we're gonna add up to 1. So that means that checks out. So this is a legitimate probability model. Ooh, if I could talk. Find the probability that a chosen student is not in the traditional age group, which is 18 to 23, okay? So the probability of not 18 to 23 is the same thing, the 1 minus the probability that they are 18 to 23, okay? So I'm gonna write out the notation because I think the notation is important to grasp and understand. In the grand scheme of things, it's gonna boil down to the fact that you be able to show your calculation on the AP exam. However, this is one of those things that Mr. Dottie's going to require you to write out a probability statement. So that's the way it goes. Anyway, so the likelihood of being in that 18 to 23 category is going to be this 57 that we pull from there. And so that means that not 18 to 23 or non-traditional is going to be 43%. Okay. Example 2, sloths are the slowest moving land and mammals in the world. In fact, they move so slow that algae can grow on their furry coats. Data has been collected on 2 variables, gender and whether they have large algae growth on their fur. The two-way table is shown below. Suppose we choose a sloth at random. Find the probability that each sloth has probability growth. So first of all, we need to have some totals here. So we have 100 male sloth. And it looks like we have 100 female sloths, so for a grand total of 200 sloths in our table. If we add down, I have 72 that had algae, and then I have 128 that do not have algae. So most of the time, we're going to need to have some totals in order to make a calculation here. All right, so probability of algae. So we're going to say that's a probability of A. If I come over here, 72. You can't see my pen. The probability, we have 72 favorable events. So that means that we're going to have 72 out of 200 total in my table. So that's going to be a 0.36. Also, in reality, if you write 72 out of 200, a fraction is fine. We probably ought to reduce that down to whatever that's going to get reduced down to. I don't know. 36 out of 100, and then 18 out of 50, and then 9 out of 25. So you could reduce that down to 9/25. However, I think it's just as simple to write it as a decimal. A male with algae growth. It's a male and algae. So there are 30 males that have algae. So again, we're going to grab my males with algae. They're right there. That's what I'm looking at. These 30 right here. And then we're going to divide that by 200. And that's going to be 0.15. And lastly, is a male or has algae growth. And I think I have failed you. I have failed you. I failed you. I failed you. So let's come back up here and talk about how I failed you. I failed you because I did not talk about our general addition rule for 2 events. Okay. So what happens is, I'm going to add, if I have the probability of A or B, which is what that statement is reading right there, That means it's the probability of A plus the probability of B minus the probability of both, okay? So if we talk about that really fast, why we have to do that, golly, I feel like I'm killing time here. But let's say we have we have jacks. So there's my circle of jacks. We have the jack of hearts, we have the jack of clubs, we have the jack of spades, and that leaves me with the jack of diamonds. And over here I have diamonds. So we have the ace, we have the 2, the 3, the 4, the 5, the 6, the 7, the 8, the 9, the 10. We got the jack covered, we got the queen, and we got the king. Okay, so there's all my events that are total possible. So I want to know, what is the probability of it? The probability of a jack. Okay, there's 4 jacks. Okay, the probability of a diamond. Well, if I counted all those, there's 13 out of 52 in there. Okay, so the thing I want to find out is, what is the probability of a jack or a diamond? Okay, well, if I add those together, if I say that that's just the probability of a jack plus the probability of a diamond, let's see what we have here. A jack is 4 out of 52, and a diamond is 13 out of 52. So that looks like it should be 17 out of 52, which is wrong. So if you don't want to write that down, don't, or we'll talk about the adjustments I have to make here in a second. Okay, but if I look up here and I grab my highlighter and I count, there's 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, 11, 12, 13, 14, 15, 16. There's only 16 events up there. Well, there's 16 events up there, but if I come down here, I just said that there's 17 total events. All right, so anybody know why we ended up with counting 16, but I added up 17? What's our flaw up
one
there?
Of them twice.
Yes, the jack of diamonds. I ended up counting it with the 17 here, I ended up counting the jack of diamonds twice. So that is why in my general addition rule, I'm going to add those two together. Now, if my events are disjoint from the very get-go, then the intersection of those two is going to be 0. Okay, meaning if I had done this same exercise with jacks and aces, since there's no jack of ace, they are disjoint events, then I would not have had to worry about subtracting off that 1 out of 52. I have to subtract off that intersection to get 16 out of 52. I never finished that example. So in the previous one with jacks and diamonds, I have to subtract off that intersection, which is 1 out of 52. So that's where we get 16 out of 52. That's no good. Okay, we don't have to worry about this if I have disjoint events. So with all of that ribble rabble said, back to males or algae growth. So let's talk about how that looks notation wise. Again, it's one of those things where I like the notation, but this is where I think the notation actually becomes cumbersome, but we'll do it. So my notation looks like this. I'm going to have a male or, so that's where we get that union sign, algae. And if I use my general addition rule, this is the probability of being male plus the probability of having algae minus the likelihood of both male and algae. So that's what the notation of it looks like. In reality, you can do this probably pretty simple. I mean, we'll talk about how we can do it simpler, but males. So I ended up with I haven't done that yet. I don't have that probability, but there's 100 males out of 200. So we have that. We already did algae above on problem A, which is going to be 72 out of 200, minus the likelihood of both, which we calculated already as well, to be 30 out of 200. And so since they're all out of 200, that worked just fine. We end up with 142 out of 200. So that ends up being a 71%. Okay. In reality, I'm probably not doing that. If I'm looking at this problem, again, notation, I want the notation on my test, but if I'm taking the exam, I'm looking at it this way. I need 2 things. I need males and I need algae. So if I'm doing this, I'm taking all these males, which is 100 males. So let's see here. You can't see I'm taking this row right here. I have 100 males. But then I need to add on my people. But if I'm doing algae as well, I have males and I have algae. Well, I'm double counting those 30. So that's why I had to subtract that off. Or if I wanted to, I could just take this 100 here of males and add on my females with algae. So 100 plus 42 gives me this 142 that I used there. So you don't always have to use a formula and just get bogged down in that. If we just use some logic, sometimes that just works as well. Okay. All right. So on to the next problem. I have over-talked this and we're not going to get done. If I add up that row, we get 417. If I add up this row, oh man, there's so much space here. 2839. That's going to be impossible to see. I'm sorry. And so my table total is 3256. My column totals are 928. And 1329. And it's also one of those things of you may not, there's no sense in getting all the totals up front. You could just go for the totals that you need. But I just like to have everything up front. So find the probability that a study was performed to look at the relationship between motion sickness and a seat position on a bus. The following summarizes the data. So we can sit in the front, the middle, or the back. Those are my seat positions. Okay. We could have nausea or no nausea are my other ones. So if we go here, we're finding the probability that the person gets nausea. So favorable outcomes. If we come over here and look at the table, nausea is going to be this 417 here out of 3,256 people that we asked. So that's what we have. 417 out of 3256. And so we're going to roll in with a 0.1281. Find the probability the person is in the middle and does not get nausea. So again, we haven't established variables, so we'll just write this one out. We got middle and nausea. Probably spelled wrong. Yeah, there's no U on there. All right. Anyway, it's a middle. So again, finding what number I need, we have middle. So I'm talking about this column. We're going to get nausea, so that's 1163. Okay, so back to my pen, if that message would leave. 1163 divided by 3256, and that's going to give me a 3572. Okay, and we're rolling right along. On page 3, Venn diagrams, those are my favorite kind to do. We just need to go through a little bit of a notation here. So we got to talk about the complement of something. And again, this is can be expressed in different ways, but we're going to go with that. So if I have event A in the center, its complement is going to be everything that's not in the center. So a complement. Okay. Again, a little pictorial thing. We have events A and B. A and B are mutually exclusive if they have nothing in common. So if I were to look at that in Venn diagram form, here is A and B. So this is going to be my yellow M&M and my blue M&M. Okay, they cannot be the same color of M&M at the same time. Okay, this is my blood types. Actually, this works for blood types. I have a type A and a type B. I can't be the same. I can't be. Yes, we can have AB blood type, but that's not the same. The AB does not belong to the group A or the group B. It's its own blood type. Okay. The intersection, again, notation wise, this is A intersect B. So that means we're looking at, this is going to be event A. This is going to be event B. What we're looking at is this shaded region is going to be the intersection of those two. Okay. So again, trying to understand notation and terminology. That's what we're looking for. Okay. The union of two events, A union B. So here we go. Again, here we have event A, we have event B. In a union, I want absolutely everything. So we want A only. We want the intersection of the two, and we also want B only. So we want all of those. Those are going to be it's a combination of everything within my Venn diagram. All right. The weather forecast shows the probability of rain tomorrow is 40%, while the likelihood of wind is 6%. There's a 3% chance that it's going to be both windy and rainy. So we're going to practice doing a Venn diagram for this. So in our Venn diagram, We're going to have two events here. We have wind and we have rain. And it tells me that the likelihood of rain tomorrow is 40%, while the likelihood of wind is 60%. I don't know what I was trying to draw there. And there's a 30% chance of both. So we're going to put that 30 in the middle. Now, from here, we're actually going to find in a Venn diagram, there's 6 spots that we're going to find. It just varies depending on the problem of what we're given. This is the most basic and simplest one. So what we're going to find here is going to be this guy right here, which is going to be representing wind only. Likewise, this one here represents rain only. And what is this guy out here going to represent? This is going to be no wind and no rain. Okay, that's the other pieces that we can find. So that means that what happens is we know that this circle is 60%. However, we have 30% already burned up here in the intersection. So that means if we take 6 minus 0.3, we're going to get another 0.3 there. If we take 0.4 minus 0.3, that means that we're going to have a 10% chance of rain only. Okay. So now it's figuring out what then is out here in the no wind and no rain. So we have 30 and 30 to give me that 60%. We're going to add one more onto that. That's 70%. So unfortunately, this is a really ugly problem. I should change that because there's too many 0.3s out here. But if there's a 70% chance of wind or rain, that means there's a 30% chance of no rain. So what is the probability that there will not be high winds in this locality tomorrow? Okay, so again, if we just get in, just to work in the practice of the probability statements, the probability of not wind is going to be 1 minus the probability that there is wind. So that means that there's a 60% chance that it's windy tomorrow. So that means there's a 40% chance not windy tomorrow. Are wind and rain disjoint events? Again, disjoint means they cannot happen at the same time. So can I have wind and rain at the same time? Well, yes, I can. So that means that they are not disjoint. Are wind and rain independent events? Okay, so this is the part that we haven't gotten to because conditional distribution is actually in the next set of notes. And now I have to decide, I've hit that fork in the road. Am I going to go flip over there and do conditional or not? So I believe in both of these cases, I believe I need to. So we're going to flip to the next, not the next page of notes, but 2 pages from notes from now. And we're going to look at this conditional probability. Okay, so here's our formula for a conditional probability. It is the likelihood of event A. So if I have the notation looks like this, the probability of A given B, and then it's going to be into to calculate that, it's the intersection of A and B divided by the likelihood of B happening. So I'm going to go to the other page and we're going to write out a little different definition over here beside this. So we have the probability of an event and a condition. Okay, that's my conditional probability. So what happens is to calculate this conditional probability, it's the probability of both divided by the probability of the condition. Okay, now this is the part where we're missing a little bit of notes here, so I should change this to a different spot. So I want to know, what is the likelihood that it rains given that it's windy. We'll just start there. Is that the one I want to do? Sorry, I am going to follow my notes that I have here, and I have it the other way. So the probability that's windy given that it's rainy. Okay. So that means that if we're trying to find this conditional probability, it's the probability of wind and rain divided the probability of the condition, which is rain. So we have moved from a very vocabulary-based, non-mathy unit of experimental design to a very mathy unit. A lot of number crunching in this unit. So those of us that didn't appreciate the non-mathiness of experimental design, we're going to go to the other side of this curve. All right, so the probability of having wind and rain. So we have that up there. It's really hard to pull because there's three different 0.3s, but it is this guy right here. It's the intersection of the two. This is wind and rain both happening at the same time. Out of all the probabilities, here's a 0.4. So I need to flip that out of here so I can grab my pen and get a 0.4. So that means that the probability is 0.75. Now the thing is, we have not even answered the question that it wanted to know yet. It wants to know, are these independent events? So I just calculated a conditional probability, the probability of wind given rain. What I want to do then, I want to compare that to, does that equal the probability of wind only? So I want to see, does the existence of rain increase or decrease the likelihood of it being windy? That's what I'm determining here. Okay. This is really ugly because we haven't really talked about independence yet. So we're using a problem to talk about independence. What was the probability of it being windy was 0.6. However, the probability of it being windy, given that it's rainy, we just found out to be 0.75. So therefore, the likelihood of it being windy has increased since it is raining, which kind of makes sense. So therefore, they are not independent. Okay, and I barely squeezed that in there, but anyway, there we go. All right, I feel like I'm probably put half of you to sleep, but we'll see. Suppose that you wake up and hear high winds outside. So this is going to be a conditional probability. You wake up and you hear high winds. So that means that we have a condition, it's windy. What is the probability that there will be rain? So this is a very similar calculation, except now the condition is it's windy. Beforehand, we did the condition it was rainy. So now it's windy. So what I need on top, I need, and again, we can get, I lose a little bit of the probability stuff. We need rain and wind divided by wind is what we're looking for. So again, if we go to my Venn diagram, we have wind and rain. We have a 30% chance of that happening. Divided by wind. Well, wind was 60%. Now I know the common mistake is to grab this wind right here, okay? But we're looking for the wind total, so that's why we get that 0.6. So we get a 50% chance. So you wake up, you hear it is windier than heck outside. There's a 50% chance of rain. Okay. And again, that verifies that it was not independent because rain in general is up here at 40%. So the likelihood of rain has increased because I heard it was windy outside. All right, I think we've got a couple more example problems to try to walk ourselves through, and then we're going to be stopping for the day. So this won't be horribly bad. We'll just see how long it takes us to get through this. Anne has applied to both Cornell and Purdue University. Suppose that the probability that Anne is accepted to Cornell is 0.4. The probability she accepted to Purdue is 0.5. The probability she accepted to both is a 0.2. So maybe now we can have, no, this one's not, but I should go back and change these notes. We got too many repeat numbers. Anyway, we have two events. We have a Cornell and we have a Purdue. The Cornell was 0.4. The Purdue was 0.5. And the likelihood of being accepted to both is a 0.2. Okay, So again, if we come over here, we can go ahead and fill out the rest of my Venn diagram. I know that this little number right here has to make the circle 0.4. So we're going to take 0.4 minus 0.2, and this is going to give me a 0.2. Likewise, this entire circle is 0.5. I've burned up 0.2 here in the middle, so that means that the other part of this is going to be 0.3, because between the two, they're going to add to 0.5. And lastly, we're going to have the part that she got rejected by both universities. If I add the interior together, if I add 0.2, 0.2, and 0.3 together, that's going to give me a 0.7. In reality, what you could do is you could just add the 0.4, because it's this circle with 0.3, add those two numbers, we get a 0.7. Or if we added those two numbers, we also get a 0.7. So you can add three numbers, add two numbers, whatever works for you. All right, so anyway, that's 70%. So that means if there's 70% in the circle, that means there has to be 30% outside the circle, which means I am not accepted to either, or Ann is not. Okay, so A, what is the likelihood that I'm not accepted to either university? That's also going to be the 0.3. We found that in the Venn diagram. Okay, what's the probability that Ann is accepted to Purdue but not Cornell? All right, so here's my Purdue circle. Here's Cornell, but here's not Cornell. So again, that answer is also a 0.3, but it's this 0.3 instead. Okay. We haven't gone over our independency rule, have we? Wait, are the events of sorry, I guess I should read. Are the events accepted to Cornell and accepted to Purdue independent events? Okay, so here we go. We have to have an explanation. So this is what we're gonna do. We're gonna make a comparison statement. So this is the probability of being accepted to Purdue. We know that. What's the probability that we get accepted to Purdue? That's gonna give me a 0.5. What I want to compare that to see if they're independent is the probability of being accepted to Purdue, given that I was also accepted to Ann was also accepted to Cornell. Okay, so that's our comparison. We want to see, does the existence of Cornell right here, does that change the likelihood of Purdue? Okay, so that's how we're going to check for independency, but we have to do this calculation now. Okay, so if I do that calculation, that's going to be the intersection of the two events. C intersect P. I should write that away the other way around, sorry. It's going to be P intersect C divided by C. So that's going to be what we're looking at. Okay, I know that the intersection of the two was 0.2. I know that Cornell, excuse me. Did I write this? Okay. Sorry, I went backwards from my notes and that confused me for a second. What is Cornell is going to give me a 0.4. And we get a 0.5. So since 0.5 equals 0.5, we're going to say yes. They are independent. The probabilities did not change. Okay, there's actually a second check for independency, is this, and we haven't gotten to this statement yet, but the probability of A intersect B is equal to the probability of A times the probability of B. That's just something we have gotten to. This is only true if independent. Okay, so occasionally we'll pull this rule out to do some other calculations. I am personally not a big fan of it myself because I think logic-wise, I think the other way is so much easier to understand. However, this is another check for independency, and it actually works here. We know what the intersection of the two is. The intersection of those two events, in this case, what's the probability of Cornell intersect Purdue, would be equal to the probability of Cornell times the probability of Purdue. So if we look from up above, the intersection of the two was 0.2. The probability of Cornell was 0.4. The probability of Purdue is 0.5, and we end up with 0.2 equals 0.2. So that's another check for independency. So it's going to be coming to your preference on which way you choose to do that. Okay, of that. What is the probability that Anne is accepted to Cornell given that she is accepted to Purdue? So she's accepted to Purdue. So it says given she's accepted to Purdue. So that is the condition. She was accepted to Purdue. What's the likelihood she's accepted to Cornell? Okay. And since we found out that they are independent, okay, I'm actually just going to go with 0.4 because they are independent events. I was going to go through this calculation, but then I realized, hey, there's no sense in going through the calculation. It's going to remain 0.4 because they are independent events. All right, we got one last example to do to try to squeeze in. Maybe this one will be, yeah, we can do this. After surveying 995 adults, 81.5% of whom were over 30, the National Sleep Foundation reported that 36.8% of all adults snored. 32% of the respondents were snorers over the age of 30. So there's my Venn diagram. We have two events here. We have individuals that are 30 plus, which is going to be 0.815. We have people that snore, which is going to be 0.368. And then it tells me that 32% of the correspondents were snorers over the age of 30. So that means we're going to have a 32 slip into this blank. Okay, so we're not going to have any issues with the different overlaps. I need to put a different one in our notes here because we're not getting the kind that only we're always given these three, and in your homework problems you're going to have some cases where you're going to be given this number out here instead, and it works differently, but that's all right. Anyway, to cut to the chase, if we take 815 minus 32, we're going to get the 495. The 368 minus the 32 is the 048. If we add all three of these numbers together, if we add the three together, we're going to get looks like a 0.863. So that means that there's a 0.137 out here that are under the age of 30 and do not snore. So anyway, that is our first question. What percent of respondents were under 30 and did not snore? That would be this 137. And lastly, we're going to ask, are they independent of each other? So again, it's how you choose to want to do this. Again, I am going to compare the probability of snoring to the probability of snoring given I'm 30 plus years old. So that's how I'm going to see if these are independent or not. Does the likelihood of snoring increase or decrease given that I'm over 30 years old? Okay, so the probability of snoring, we already have that up there. It's 368. This is going to be the snoring and 30 plus divided by being 30 plus. So if I look at the numbers I need for that, the intersection of the two events is 32. The likelihood of being 30 plus is that 0.815. And so we end up with, comparing these two things, we get a 368 and we get a 393. And so since my probability changed, these are not independent. Probability of snoring increases if over 30. Or, yeah, in 30 plus age group. Probably ought to go with how my variables are defined. So, all right, I'm going to turn the recording off.